Welcome to the lecture series on numerical methods. Currently we are discussing on numerical differentiation based on different interpolation formulas. So, in the last lecture we have discussed this numerical differentiation based on Lagrange interpolating polynomial. In the Lagrange interpolating polynomial we have discussed this numerical differentiation at tabular points, and in this lecture we will discuss about this numerical differentiation at the non-tabular points, but within that interval only. Within that interval means if you will have these tabulated points like x0, f of x0, x1, f of x1, xn, f of xn, then if we want to find the derivative at a particular point which should lies between like x0 to x1 within this interval or x1 to x2 within this interval. So, somewhere maybe it is just lying, and at that point we want to evaluate this differentiation. And for that, if you will just consider first example, like suppose we will have these data points are x is prescribed at like 0, 2, 4, 5 suppose, and its functional values are like 5, 9, 85, 180 suppose, and corresponding Lagrange interpolating polynomial if we want to write, so it can be represented in the form of like p and x equals to summation k equals to 0 to n lkx f of xk, where lkx can be represented as omega x divided by x minus xk omega dash of xk here. So, basically for this problem if you will just write here omega x, so omega x can be written as x minus x0, x minus x1, x minus x2, x minus x3 here. Since we will have here 4 points, it can construct a polynomial of degree 3 here. So, we can just write p3 of x, that is your L0x f of x0 plus L1x f of x1 plus L2x f of x2 plus L3x f of x3 here, where this omega x, if you will just consider this particular problem here, this can be written as x minus 0, x minus 2, x minus 4 into x minus 5 here. And if you will just write here L0x, and L0x can be written in the form of like x minus x1, x minus x2, x minus x3 divided by x0 minus x1, x0 minus x2, x0 minus x3 here. And at particularly this tabular points, we can just write this one as x minus x1 is here, since especially we are just defining this is as x0, this one is x1, this is as x2, this is as x3 here. So, if you will just write all these points here, that is as x minus 2, x minus 4, x minus 5 divided by your x0 is 0 here. So, 0 minus 2, 0 minus 4, 0 minus 5 here. Similarly, we can just write L1x also. So, if you just write L1x here, this can be written as L1x as x minus x0, x minus x2, x minus x3 divided by x1 minus x0, x1 minus x2, x1 minus x3. So, directly if you will put all these values x minus 0, x minus 4, x minus 5 divided by x1 is given as 2 here, 2 minus 0, 2 minus 4, 2 minus 5 here. Similarly, L2x can be written as x minus x0, that is as 0 here, x minus x1, x minus x3 divided by 4 minus 0, 4 minus 2, 4 minus 5 here. Similarly, if you will just write L3 also here, so L3x can be written as x minus 0, x minus 2, x minus 4 divided by 5 minus 0, 5 minus 2, 5 minus 4 here. And particularly if you have determined this L1x, L2x, L3x and L0x on these tabular values, so then we can just obtain the first order derivatives of this Lagrangian coefficients as L0 dash x can be written as, so first product if you will just consider here that is in the form of like x minus 4, x minus 5 divided by all of these product terms, that is minus 2 into minus 4 into minus 5 here. So directly we can just write that one, and minus 2 minus 4 into minus 5 plus second term if you will just differentiate here, x minus 2 into x minus 5 divided by minus 2 into minus 4 into minus 5 here. Similarly, the last term if you will just differentiate here, x minus 2, x minus 4 divided by minus 2 into minus 4 into minus 5 here. And similarly, if you will just differentiate L1 dash of x here, L1 dash of x can be written as like first term if you will just differentiate here, so x minus 4, x minus 5 divided by 2 into minus 2 into minus 3 here plus again x into x minus 5 divided by 2 into minus 2 into minus 3 plus last term if you will just differentiate here, x into x minus 4 divided by 2 into minus 2 into minus 3 here. Similarly, L2x if you will just write it down, so L2 dash of x can be written as your first term if you will just differentiate, then x minus 2 into x minus 5 divided by 4 into 2 into minus 1 here plus second term if you will just differentiate, x into x minus 5 divided by 4 into 2 into minus 1, last term if you will just differentiate, x into x minus 2 divided by 4 into 2 into minus 1 here. And similarly, we can just obtain this derivative for L3 dash of x also here. So if you will just write L3 dash of x here, so L3 dash of x it can be written as x minus 2 into x minus 4 divided by 5 into 3 into 1 plus second differentiation if you will just take, x into x minus 4 divided by 5 into 3 plus last differentiation, x into x minus 2 divided by 5 into 3 into 1 here. So if you will just consider here x as a 3, then we can obtain L0 dash of 3 here. Then if you will just consider L1 dash of 3 here, then we can just obtain the value of L1 dash of 3 here. L2 dash of 3 we can just put x as 3 here and we can obtain the value, and L3 dash of 3 we can just obtain the values by putting x as 3 there. So if you will just put all these values, then we can just obtain that L0 dash of 3 as 1 by 40, L1 dash of 3 as minus 7 by 12, L2 dash of 3 as 5 by 8 and L3 dash of 3 as minus 1 by 15 here. and once these values are known to us, like if you just write here, this value is just giving you like that, especially we are just writing here y dash of 3, since it is asked to find here. So, we can just write this one as L0 dash of 3 into f of x0 plus L1 dash of 3 f of x1, L2 dash of 3 into f of x2 plus L3 dash of 3 f of x3 here. So, if you will just evaluate or put all these values here, then first value if you will just write, so L0 dash of 3, it is just found it as 1 by 40 here, and L1 dash of 3, it is just found as minus 7 by 12 here. L2 dash of 3, it is just found to be 5 by 8 here, and L3 dash of 3, it is just found to be like minus 1 by 15 here. And directly all of these functional values, that is given as f of x0 as 5 here. So, if you just put all of these values, we can just write this one as 1 by 40 into f of x0 here 5 plus minus 7 by 12 into 9 plus 5 by 8 into 85 minus 1 by 15 into 180 here. And if you just do this computation, especially you can just get the value as 36 here. So, then we will just go for this differentiation using Newton's divided difference formula. And in Newton's divided difference interpolation formula, already we have known that the advantage for this Newton's divided difference formula is that in case of Lagrange interpolation formula, if a small quantified quantity it should be associated with this interpolation formula, then always we will just go for a large multiplication of these factors. But in divided differences, that we can just overrule that factors. So, especially if a term is asked to associate, in that terms directly we can just write a multiplication and we can just evaluate that one. So, here in a like Newton's divided difference interpolation polynomial, we will have like the set of tabular points, that is S, xi and f of xi defined at n plus 1 points like x0, x1 up to xn points. So, if you just write this in Newton's divided difference interpolating polynomial, that can be represented as Pnx equals to f of x0 plus x minus x0 f of x0 x1 plus x minus x0 x minus x1 f of x0 x1 x2 up to x minus x0 x minus x1 up to x minus xn minus 1 f of x0 to xn here. So, if in a complete form we want to write, or in a product form if you want to express, or in a sum form if we want to express, then Pnx can be written as summation of I equals to 0 to n f of x0 x1 to xi product of j equals to 0 to I minus 1 x minus xj here. So, if we want to find the derivative for this polynomial here, this polynomial derivative can be written as Pn dash x here. This equals to summation I equals to 0 to n. Since all these values are constants here like f of x0, x1 to xi, then we can just write this derivative as here d by dx of product of j equals to 0 to I minus 1 x minus xj. And all of this tabular values, it is known to us, and the associated functional values are also known to us. Then we can just use these functional values to calculate this derivatives with respect to x here. First, for this we will just consider a linear interpolation here. In case of a linear interpolation, we have to consider only 2 points where these tabular points may be x0 f of x0, x1 f of x1. And if we will just consider this linear interpolating polynomial using Newton's divided difference interpolation here, then we can just write this polynomial as P1x, this equals to f of x0 plus x minus x0 f of x0 x1 here. Since we are approximating the function f of x with polynomial of degree 1 here. So, always we can just remember that if we will have a polynomial of degree n, always we should have to consider n plus 1 terms there. So, if we are just approximating this function f of x with a polynomial of degree 1 here, then we have to consider 2 points, that is in the form of like y x0 f of x0, x1 f of x1 here. And if you will just consider these 2 points, then the polynomial approximation can be written as P1x as f of x0 plus x minus x0 f of x0 x1 here. And if you will just try to evaluate this first order derivative for this polynomial here, so P1 dash of x can be written as, since first term if you will just see that this argument contains only a constant point here, hence we can just write P1 dash of x as f of x0 x1 here. And if you will just consider like a quadratic interpolation suppose, so then we will have like 3 points we have to consider for quadratic interpolation, since it represents a polynomial of a degree 2. So, 3 terms at best it is required. So, if you will just consider this quadratic polynomial here, the quadratic polynomial associates the points like x0 f of x0, x1 f of x1, x2 f of x2 suppose. Since 3 points are required, so that is why we have just considered here 3 points as x0, x1 and x2 here. And if you will just approximate this one with a polynomial of degree 2 here, this polynomial can be written as P2x as f of x0 plus x minus x0 f of x0 x1 plus x minus x0 x minus x1 f of x0 x1 x2 here. If we want to find this first order derivative for this function P2 of x here, so this can be written as P2 dash x as first term, this can just give you 0 value, and second term if you will just consider here, that can be represented as f of x0 x1 here, and immediate next term if you will just consider, that can be written as 2x minus x0 minus x1 into f of x0 x1 x2 here. So, based on this, if you will just go for a example here, then we can just write this tabular values as like compute suppose y dash 3, y double dash 3 from the tabular data like 1, 2, 4, 8, 10 suppose the functional data is given, and this tabular data is given, and the functional data are given like 0, 1, 5, 21, 27 suppose. If you will just write this tabular data, that is in the form of like 1, 2, 4, 8, 10 suppose, and the functional values are like 0, 1, 5, 21, 27, and it is asked to compute y dash of 3 and y double dash of 3 from the following table. Compute y dash of 3 and y double dash of 3 from this table. So, first we will just use this divided difference table formula to get all this difference data there. So, like first difference, if you will just find here, this can be represented as 1 minus 0 by 2 minus 1, since it is the formula especially. So, the first order difference we can just write here 1 minus 0 by 2 minus 1. Second one, if you will just consider 5 minus 1 divided by 4 minus 2 here. Third one, if you will just consider 21 minus 5 divided by 8 minus 4, and last 2 points, if you will just consider 27 minus 21 divided by 10 minus 8 here. Obviously, we can just obtain the data as 1, 2, 4, 3 here. And in the second difference or second divided difference, we can just write this data as 2 minus 1 divided by 4 minus 1, then we will have like 4 minus 2 divided by like 8 minus 2 here, then last value, if you will just consider here 3 minus 4 divided by 10 minus 4 here, 10 minus 4. So, obviously, you can just obtain these values as 1 by 3, 1 by 3, and last value this will be minus 1 by 6 here. And next third difference table, you can just obtain these values as 1 by 3 minus 1 by 3 divided by some of this data like 8 minus 1, and then 1 by 3, sorry, minus 1 by 6 minus 1 by 3, 10 minus 2 here. So, this can first value you can just get it as 0 here, and second value you can just get it as minus 1 by 16 here, and fourth divided difference you can just find minus 1 by 16 minus 0 divided by 10 minus 1 here, and you can just obtain this one as minus 1 by 144. And if you will just use this Newton's divided difference interpolation formula for this calculation of these values here, so we can just use these values, that is 0, 1, 1 by 3, 0, minus 1 by 144 as the tabular values here. So, maybe in the next lecture we can just continue that how we can just use this Newton's divided difference formula for finding this derivative. Since I have just given you a recount of this Newton's divided difference, that directly we can just use these formulas for the derivation of the data, and I can just consider the same example in the next lecture, and I can explain that how we can just put this data in the tabular form and we can obtain the first order derivative or second order derivative in a complete form. Thank you for listening the lecture.